Hiya, in this video we're going to convert from binary to decimal and from decimal to binary, so we may as well get cracking. Hopefully you've seen the other videos in the playlist which explain the binary and other number systems positional columns and what they're worth. If you haven't watched those, then you could watch them, otherwise we'll just carry on anyway. So you may be asked to convert a binary number, and someone might say, right, in binary 101101101, and they might say, right, convert that to decimal, and you're thinking, what? Like, how on earth would you do it? And all you really have to do to start with is put the number into the columns where they each belong, knowing that the first one on the right is the units, and every other one is then twice as big, 2, 4, 8, etc. But we'll do this a bit neater. Can't remember what the number was, but I don't really care. If someone says to you, I don't know, convert 10101 in binary, obviously we'd normally like write a little 2 there to show the base. Convert that to decimal or base 10. You go, alright then, well, because this could be in base 10, 10,101, but we know it isn't because we put the little 2 there, subscript, which says it's binary, so this column isn't the 10s, this is the 2s column. So all you do, first column is your units, and then because it's base 2, you multiply by 2 every time the column is on the left. So it's 2, and then 2 times 2 is 4, times 2 is 8, and times 2 is 16. If you've been given leading zeros, like here, if someone had said start with a 0, then there's no point. We don't care about leading zeros. We don't put zeros in front of numbers unless the 0 is the units and there's a decimal point, but it's not like that with this number. It just starts with a 1. So forget any leading zeros, and obviously any zeros after the decimal point, but we all know about that anyway. So now we've put the number into like its place value, it's really easy to convert binary now into base 10. All you do is multiply and add. Like the number 37 in base 10, we know that's the units, that's the tens. We say it's 3 times 10 added to 7 times 1, which is 30, and 7 is 37. And all we do is the same thing with binary, but here we've got one lot of 16, so really technically we would say 1 times 16, I wrote that backwards for some reason, 1 times 16 plus 0 lots of 8. But what's the point of writing 0 lots of 8, because we know it's 0 anyway. Let's just move on to the next column. Plus 1 lot of 4, so 1 times 4, plus 0 2s, don't bother writing 0 of something because it's 0, plus 1 lot of 1. So that is equal to 16 plus 4 plus 1 is equal to 21 in base 10. So we've converted from binary to decimal, and it was really easy. But we did it like the long way, just to show all the working out. Really, all you really say is wherever there's a 1, you add one of that number. So it's 16 plus 4 plus 1, because they're the only numbers with 1s in. You forget all the 0 ones because it doesn't matter. What's the point in adding 0 of something? Okay, so it's as simple as that really, but practice makes perfect. So let's do, I don't know, 1 1 1 0 0 1 0. I don't know what that is. So all we need to do is continue what each column is worth. If that's a 16s column, this must be 16 times 2, because it's the base 2 number system, and then this must be times 2 again. So now we've got, that's worth 64, that's worth 32, that's worth 16. That column, 0 lots of 8 is 0, 0 4s is 0, 1 lot of 2 is worth 2, and 0 1s is 0. So now we've got these numbers to add up. But what you'll find is there's lovely like number bonds in binary. For instance, 64 and 16 that adds up lovely to 80. And then we've got 32, so that would be 80 and 20 and 12, which is 112. And the 2 is 114. So all we can say from what we've learned so far is the top number 10101 in base 2 is equal to 2 tens and 1 unit in the other number system. And we can also say that 1110010 in binary is worth 114 in base 10. So that's about as hard as it ever gets. I suppose you may have fractions, you know, they like to make things harder just for the sake of it, don't they? So you might have 1010.11, and all you really need to do again is shove it into the number system, the columns. We know that that 0 to the left of the radix point is the units, so that's the 2s, that's the 4s, that's the 8s. Radix point, we can't call it a decimal point because it's not base 10, it's not a decimal number system. So this is the halves and this is the quarters. So this number is worth 8 plus 2, because they're the only ones that have ones in their column, plus a half plus a quarter. And it doesn't take Einstein to work out that that's equal to 10, and a half and a quarter, well a half is 2 quarters, 3 quarters, so it's 10 and 3 quarters, or 10.75, whichever way you want to put it, in base 10. And that's about as hard as it gets. So now you are hopefully proficient on going between binary and decimal. And in the next bit of the video we'll go from decimal to binary, which is a little bit harder but not much. All we do going from binary, we multiply and add, and going to binary from decimal, we divide and subtract pretty much. So they're kind of like inverse operations. Alright, so we've done binary to decimal, so let's do the other way around. Let's start with a decimal number and convert it to binary. And it's just as easy if you follow the process. It's the same as anything, isn't it? You follow the process for maths and you get the right answer, and that's it really. So this will be the decimal to binary, or the base 10 to the base 2. It's so easy when you know how, but this is how. If you get a number, say, I don't know, 400 in base 10, we know that that's worth 0 units, 0 tens and 400s. That's why it's 400. We only put the zeros there to push the 4 over, otherwise it would be worth 4 if it was stuck there. So it's a positional number system, and we're going to convert from 400 in decimal, that's equal to, I don't know, how much in binary? Well, that's what we're going to find out. First thing to do, figure out how many binary columns you need to actually represent this number. So 400 is definitely bigger than the units column, it's definitely bigger than 1, and then the next column is 2, it's bigger than that, it's bigger than 4, it's bigger than 8, it's bigger than 16, it's bigger than 32, it's bigger than 64. It would be, wouldn't it? So typically I'm going to have to move all this over and put more columns in, for, you know, that's the kind of guy I am, I don't mind. So there we are, we're laughing now. So 400 is bigger than the next column, which is the 128. Double it again, because it's base 2, 256. Double it again, 512. Now you might ask yourself, let's just check they're right. 1, 2, 4, 8, 16, 32. Double, 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 that's right. So we know these are correct. But do we need the 512 column to represent 400? Could we ever put a 1 there? And no, we can't, because 400 is less than one lot of 512. So we could only ever put a 0 there. So what's the point in having a leading 0? If you're 21 years old, you don't say you're 021, do you? You just say you're 21. So we don't bother with leading zeros. So we don't bother with columns that we don't need, unless we're stuck to a certain bit length, like in a computer architecture is always 8-bit or 16-bit or Windows 32 or Windows 64. Then you have to have a value for every single bit. But we're not stuck to computer hardware here, we're just talking about general number systems. So we've got 400, base 10. How do we work out what it is in binary? Well, what you do, you divide by the largest column. So step 1 is going to be our number 400 divided by 256. How many 256s are there in 400? But we also know that in binary we can only use the digits 0 and 1, so we know there's not going to be two lots of 256, otherwise there would have been a 1 in the 512 column. But anyway, so there we go. 400 divided by 256 is equal to 1 point something. Okay, it's less than 2, but it's more than 1. So what we do is 1.7. I'll work out the exact figure. Let's have a look. Could do with a calculator. Oh, there we are. That's nice, isn't it? So we say 400 divided by 256 is, oh, that's nice, 1.56. Alright, so it's equal to 1.56, but we don't care about the 0.56. We can't write 1.56 here. All we can write is 1. So it's definitely one lot of 256. So out of that 400 so far, we've represented 256 by putting the 1 there. So we need to figure out what's left of our number. So we do the original, take away 256. Well, to get to 300 would be 44. So to get to 400 is 144. So this is our new number now. We don't care about 400 anymore. You see later, we don't care. We've got a new number which is 144, and we need to figure out where that fits in all of these other columns. So basically the next step, step 2, is 144 divided by the next biggest column. So that's going to be 1 as well. And 1 times 128 is 128. So what we've got left, having represented 256, and also we've represented another 128 out of our 400, we see what's left. 144 take away 128. Well, if you added 10, it'd be 138 and another 6, so that's 16. We've got 16 left. So now we don't care about the 144 either. All we've got left is 16 to stick somewhere in here. But we can't put 16 in the 64s column. We couldn't put a 1 there because that would be one lot of 64, and we've only got 16 left. So 16 doesn't fit in there. We couldn't put a 1 there because 16 is less than 32 as well, so you have to put 0. Oh, here we are. We could put a 1 there because 16 is exactly one lot of 16, and now basically we've got rid of our remainder because we've represented it here. So we know all the other numbers, all the other columns, have to be 0. So we're finished. Happy days. Hashtag the Fonzie. So we've gone from 400 in base 10 is now equal to a base 2 number, which is 11001000. Happy days. I'll draw a little face. There we go. We now know how to go from decimal to binary, and we always use the same way of doing it, and I hope it's been enlightening. And in the next video we'll do octal to decimal and decimal to octal, then we'll do hex to decimal and decimal to hex. Alright, thanks for watching. Cheers.